Hello, welcome back to Digital Circuits, and today we will be learning about Boolean Algebra. Specifically, the axioms and rules of Boolean Algebra and how we can use it to our advantage when building digital circuits. I'd like to start us off with a quick reminder. Boolean variables, or any numbers in Boolean Algebra, can only be 0 or 1. This is important, as 0 means that that particular signal is off, and 1 means that particular signal is on. This will help us manipulate Boolean algebra in such a way to help us build digital circuits. I'll start us off by defining a variable x. Now, the variable x is a Boolean variable, which means it can only be 0 or 1 or on and off. Let's use x to examine some of the laws of Boolean algebra. Alright, let's start by examining some properties of the OR function or addition. Let's start with x plus 0. What might x plus 0 be? Well, let's take a look at all the possible combinations. 1 plus 0 will equal 1. This makes sense. 0 plus 0 will equal 0. We know this from regular algebra. Using these two facts, we find that no matter what the other input is for the OR function, as long as one of the inputs are 0, the other input will end up being our output. Or in other words, x plus 0 always equals x. Alright, we have our first axiom, x plus 0. Now let's examine addition or the OR function if one of the inputs were 1. What does x plus 1 equal? The first case is when x equals 1. 1 plus 1 in Boolean algebra equals 1. This is because you can't get more on than on. I've mentioned this previously. Now, let's check out 0. 0 plus 1, as we know, equals 1. So no matter what one of the inputs is, the output will always equal 1. Alright, we have two complete rules for our OR function. Now let's show some love to our AND function. Here, we've got x times 0, so let's analyze all the cases. In both Boolean and regular algebra, anything times 0 equals 0. So, we get that x times 0 equals 0. Finally, let's examine 1 times x. Boolean and regular algebra are similar in this regard, in that anytime you multiply something by 1, you get itself. So, x times 1 naturally would be x. Alright, now that we have 4 rules down, I'd like to examine something slightly different. Let's examine x times x complement and x plus x complement. These are different in that a complement is just the opposite of what x would be. So if x is 1, x complement would be 0. Alright, let's get into all the possible cases for x times x complement, starting with 1 times 0. 1 times 0, obviously, always equals 0. 0 times 1, similarly, always equals 0. This makes sense, as when x is 1, x complement must be 0, and when x complement is 1, x must be 0. This gets us to the conclusion that x times x complement must always equal 0. Alright, now let's take a look at the cases for x plus x complement. 0 plus 1 always equals 1, and similarly, 1 plus 0 also always equals 1. This makes sense as either x or x complement must be 1, and the OR function only needs one on signal sent into it to return 1. So x plus x complement is 1. Next, let's get into the commutative and associative laws. These are slightly different than what we've been doing previously, but you'll get the gist of it. I'll start by declaring 3 variables. Now, these two are pretty similar, but they're both really important, so don't get them mixed up. Let's start with commutativity. What commutativity says is that the order in which we do our operations doesn't really matter. So x plus y plus z is really the same thing as z plus x plus y. You probably knew this from regular algebra, just never really put a title to it. But now you know that it's called commutativity. Alright, now let's get into our other property, associativity. I used addition to show commutativity, so for associativity, I'll use multiplication instead. It's important to keep in mind that both associativity and commutativity hold for both addition and multiplication. Let's take a look. X times y times z equals x times, in brackets, y times z. All this really means is that it doesn't really matter in which order you execute the operations, as long as they're all executed. So in this case, instead of doing x times y times z, we do y times z first and do x later. The next property we'll be examining is De Morgan's law. De Morgan's law is pretty unique compared to all the other properties. It pretty much states that x times y in brackets complemented is equal to x. This particular property is sort of hard to prove unless you use a truth table. So To the right of the screen, I have a truth table with all the possible combinations for x and y, and I will be showing how both sides are equal on video. Alright, let's speed this up. I would like to leave one last remark before we finish up De Morgan's law. While De Morgan's law works for x times y complement, it also works for x plus y complement, in which it returns x complement times y complement. Our next property is the distributive property. The distributive property in Boolean algebra works slightly different to the distributive property in regular algebra, in that addition also distributes. Let's take a look at how that looks. X plus y times z turns into x plus y, in brackets, times x plus z. While this may look cursed or incorrect, it's actually perfectly valid in Boolean algebra. Pluses, or addition, distributes perfectly fine, just as multiplication would distribute in regular algebra. So this is the case in Boolean algebra, where it's sort of different compared to regular algebra. It's also very important to keep in mind, as it's very useful in Boolean algebra. Next, we'll do the multiplicative version. X times y plus z turns into x times y, in brackets, plus x times z. This is the same as in regular algebra, and I'm sure looks familiar to most of you. Distributive property is probably one of the most common properties in Boolean algebra, and it's very important to keep in mind. Alright, here's a list of all the properties we've looked at so far. Feel free to use this while doing homework or any given practice problems. Alright, let's try this example problem together. It says to simplify the following. X times, in brackets, x complement plus y plus 0, which equals x times x complement, in brackets, plus x times y, plus 0. Here we use distributive property. We learned from the previous properties that x times x complement always results in 0. So we can just write that as 0 plus x times y once again, plus 0. Anything added with 0, as we found out from our properties, is just itself, so we're only left with x times y. Feel free to screenshot this example and try it by yourself. Ready? 3, 2, 1. Did you get it right? Hopefully you did, and I hope you learned something new.